So I'm going to take you through the beginning of this application of equilibrium constants. I want you to notice that if you do not have any products ever, you will always shift in the direction to make those products. And if you do not have any reactants, then your reaction will shift to make up your reactant. So it's always going to shift in the direction where you have no reactant or product. But if you have some reactant and product, then you have to figure out which way you're going to shift. So you have to solve for Q, a ratio of products to reactants at some point other than equilibrium. So this is simply a matter of putting in. So let's say we go to the third row and look at the data. We write our equilibrium expression in terms of pressure, products over reactants raised to the power of their coefficients, and we put ones in. Of course, we're going to come out with 1. So what that tells us is, right now, our Q, our concentrations not at equilibrium, are greater than our K. So that means we have too many products. So we're going to shift to the left to get our ratio to come down to the K value so that it will have established the right ratio of products to reactants. If Q is greater than K, you will shift left. So you have 3 scenarios. You could be at equilibrium. You could have too many products, which means right now your Q is greater than your K, so you're going to need to shift to the left to use up some of those products and establish equilibrium. If your Q is less than your K, it means you have too many reactants or not enough products, so your reaction will shift to the right to make more of their products. So the purpose of finding Q is to determine the shift in your equilibrium. If we look at this set of data, we can see that using the same reaction, if we put in products over reactants raised to the power of their coefficients, we get a Q of 4, which is greater than our K. So our reaction would shift left to use up some of those products and turn them back into reactants. Here, our Q is less than our K, so we would shift right. And here we have the equilibrium concentrations of both reactants and products because Q matches K. So you'll have to use Q and K quite a bit. It's just one of your skills in problem solving. So the first problem is nice and simple. So this is nothing more than a little bit of algebra. You write your expression. You then put in the numbers for the variables that you have numbers for. So you have concentration of hydrogen and iodine. And you have an equilibrium constant. So it's pretty clear that you have only one missing component. So you can think of this as x squared over that times that equals that. So it's a little algebraic manipulation that gives you the concentration of HI at 3.30 molar. This is the easiest or next to easiest level of equilibrium. The easiest is we give you all of these and you just tell us K. But we can leave one of them out and you can algebraically solve for it. The second and third problem, which I thought were the same, are not at all easy. They require defining your equilibrium change in terms of x. This is a perfect square problem. So I'm going to need to talk you through this. They are not difficult, but they have a little bit of algebra. So you do have to solve for your x change in terms of a little bit of algebraic manipulation. So just hold on to this one. You're free to fill in what I have if you want. But these are, again, a little more challenging, and I want to do those in class. But if you flip over to page 29, they become pretty simple again. So this is nothing more than putting in your concentrations and solving for K. So I'm not going to talk you through a lot of these. I'm going to show you the answers, and you're going to try to achieve them. So with number 2, they have given you the equilibrium concentrations, and you write the expression and solve for K. So if you do this right, you're going to get a K of 3.59 times 10 to the negative 3. So give that a shot. Down here with number 3, this is also pretty straightforward. You're plugging in. So plug in. You should get a K of 42.19. Now you're getting into number 4, an actual problem. So those are pretty straightforward. There's not really any equilibrium involved. You're just plugging in. But with this one, again, you are solving for the concentration of NO, so it takes a little bit of algebra. So do this one for me. When you get your K, it should be 0.00574 if you do it right. On the back, I like this question. It's a good little algebra manipulation. You have these concentrations. You have a K value. You're solving for this variable on the bottom. If you do it right, you get a 10 molar solution. So prove to me you can do your algebra solving for the SO2. Then it gets into equilibrium. So I'm going to talk you through one. So these are really nice equilibrium problems. They give you your initial, and then they tell you at equilibrium you have 0.66 moles per liter of your nitrogen monoxide. So they give you this. In looking, you went from 0 to 0.66 molar. So therefore, the change was that you gained 0.66 molar NO. That means you also gained half that, since it's a 2-to-1 ratio, of your chlorine. That means you lost the same mole ratio of NOCl, but of course you lost that because the reaction was moving towards those 0 concentrations. You then simply take your 2 minus that was given, your 0 plus that, write your expression, put them in, and get K. If you look at number 7, it also gives you your initials. It gives you your equilibrium amount. I'll give you the answer to this. When you're done, you should have a K of 4.36. So that is nothing more than putting your values in and solving stoichiometrically and algebraically. Here, same thing, although I've left that one, I might as well keep that one up there. So here they gave you the equilibrium concentration of your SO2. So if you know it went from that to that, then that's your change. That's your change. Okay? So you're gaining on this side and losing on this side. Put them into your expression and you're done. And number 9 is a perfect square. So number 9, you're going to have to wait or feel free to do the perfect square. You have all of your variables in terms of x's. So if you look at this, we know we shifted our equilibrium to the right to make 2x because of the stoichiometry, to lose x and x, 1 minus x, 1 minus x, 2x. If you put them into the equilibrium expression, you have 2x squared over 1 minus x squared equals 55.3. If you take the square root of both sides, you will have a very simplified algebraic expression that will allow you to solve for x, which you can come back and put in here, and then put back into your expression and solve for the concentrations at equilibrium. So if you're not sure about this one, wait on that, but at least get it as much as I have it down on paper. So good luck to you, and we'll meet the next time in class and continue.